Hey guys, today we're going to talk about section 4.3, which deals with rational functions. So I'll be explaining what rational functions are in a second. And then we're also going to find what are called vertical asymptotes and either horizontal or oblique asymptotes of a rational function. So first off, rational comes from the word ratio, which means a fraction. So a rational function looks like this. It'll be some kind of polynomial on top, maybe a polynomial on bottom, and together this creates a fraction. So this is what your polynomial function is going to look like. The domain of a rational function is the set of all real numbers except anything that is going to make the denominator equal to 0. So that domain restriction that we've talked about in the first chapter is going to come up again because, again, we've got fractions now. So if you look at these, the first example just says find the domain of these rational functions. So this rational function you can just look at and you can tell x cannot equal -4. So it's the set of all x's such that x does not equal -4. That would be the domain. For this one, well, we're going to need to factor to figure out what the denominator looks like, to figure out what the zeros of the denominator would be, and that'll be our domain restriction. So x, factors of 12 that add up to 8 would be +6 and +2. So x cannot equal -6 or -2. Okay, so that's the domain of that. All real numbers except those two numbers. Example C, this is one of those where your x is squared and then you're adding something to it. So any input value is going to be positive because it's getting squared, and then you're adding 2 more to it, so that is all real numbers. Okay. D, this is a rational function. There is a denominator here, but there's no x's in the denominator. So there's no input that you could give that would create a 0 in the denominator because the denominator is always 3. So all real numbers for that one as well. Okay, and then the last one here, you just have an x, so x cannot equal 0. That is going to be our only domain restriction for that. Okay, so this is important that you can find the domain of a rational function, because if you have a domain restriction, so let me just take a look at this. So a domain restriction is an x value that we can never place into the function. So like for that last one, x can never equal 0. I am not allowed to put a 0 into this function as far as x values go. Now, we can get as close as we want to that restriction. So x can't equal 0, that's fine, but x can equal 0.1 or 0.0001. We can get as close as we want to 0, we just can't equal 0. So as we choose x values close to our domain restriction, our graph will turn and go towards infinity, or it could go towards negative infinity. But somehow our graph has got to turn and then head away. Think of this dotted line right here is a vertical asymptote. Okay, and in this example, x equals c. C is some number that has got to be a domain restriction. This is some number that I'm not allowed to plug into my function, so it's creating this vertical asymptote right here. Your graph is coming towards it, and then it has to turn. Think of it as like a brick wall, and as you're driving, you have to turn. You either turn right, or in this case over here, so you're turning towards positive infinity, or you could turn towards negative infinity, but you can't go through the wall. Okay? And then you're going to get closer and closer and closer and closer and closer to it, but you're never going to touch it. Okay? So that is an example of a vertical asymptote. All right, so how do we find vertical asymptotes? Well, for the most part, we're just going to do what I kind of mentioned on the first page. We're going to find the domain of the function, and if we have a domain restriction, we're going to have an issue there. Okay, now, if you look at this, it says a rational function in lowest terms, so we want to reduce. So if we've got anything common between the numerator and the denominator, we want to reduce that, and then we'll see anything that's left over, that's where we're going to have a vertical asymptote. Okay, so if x equals r, if r is some real 0 of the denominator, then that's going to be a vertical asymptote. So here's a simplified version. Factor the numerator and denominator. simplify by canceling like terms. So if there's any common terms, we're going to cancel them, and then list the zeros. These are the values where vertical asymptotes are located. If a term cancels, that's not going to be a vertical asymptote, and we're going to talk about what that is here in a second. Okay, so looking at this problem right here, the domain would be x cannot equal -3, right? So that means I'm going to have a vertical asymptote at x equals -3. So that is an equation of a vertical line. So x equals -3 is going to be my vertical asymptote, and this is where my graph is going to come towards and then turn and head away from. And that's it. So like on example B, the domain x cannot equal -2 and +2. So my vertical asymptotes are going to be x equals -2 and +2. So this graph would have two vertical asymptotes, which happens a lot. Okay. This one, well, we need the factor. I can't see what the denominator is right now. So factor xx 4, 1, plus plus. Okay. Factors of 4 that add up to 5 would be 4 and 1. So there's my factored denominator. There's no canceling. This is an x minus 1. This is an x plus 1. So both of these are domain restrictions. X cannot equal -4 and -1. And so that's where my vertical asymptotes are going to be. X equals -4 and -1. Okay? Now, last one. Let's see. Now the denominator, let me just write this over here. So I'm going to rewrite this function. I'm going to factor the denominator. This will be x plus 2, x minus 2. I'm going to factor the numerator as well to see if there's any canceling that happens. X factors of 2 that add up to 3 would be plus 2 and plus 1. Now, these two common factors are going to cancel each other. Okay? Now, that -2 is still a domain restriction. It's still an issue. So the domain for this one is still x cannot equal -2 and +2. But -2 is not going to be a vertical asymptote. The only vertical asymptote on this one is going to be the +2. So x equals +2 is going to be a vertical asymptote. Okay, so there's just going to be one vertical line that we're not allowed to cross. Now, we still have an issue with this -2. This -2 is still a number that we are not allowed to plug into this original function, okay, because it would create a 0 in the denominator. However, in this new function that we created by canceling, you could put the -2. And here's what, and we're going to do that, and I'm going to show you what we're going to create. If you have a domain restriction that does not create a vertical asymptote, instead it's going to create a hole in your graph. Okay, so we're going to have this nice graph, and then it's going to have this open circle right in the middle. It's going to have this gap, and then it's going to continue on. So what you do is you take the part of the function that is remaining, so the x plus 1 over x minus 2, which I wrote down here. Okay, so I went ahead and simplified it and wrote down here. And then we are going to input that domain restriction, okay, because it won't mess this function up, just the original function. And we're going to see what y value is created by putting that -2 in here. So -2 plus 1, -2 minus 2, and we're going to get -1 over -4, which means +1 over +4. Negatives are going to cancel out. So this input gives us that output. This x value gives us this y value. And that point is going to be a hole in this graph. So this is going to have a hole in it. So you need to factor the numerator denominator, see if there's any canceling that happens, and if there is, that's going to be a hole, and you can plug that domain restriction into the part of the function that's left over. Don't put it in the original, you'll get a 0 in your denominator, and that's not going to work. Okay? So that's the only kind of weird thing that can happen with domains, is that it can create a hole instead of a vertical asymptote. Okay? Now, your graphs can also have what are called horizontal and oblique asymptotes. Now, a horizontal asymptote is just, it's an imaginary line that your values, your functions, seems to get closer and closer and closer to as you head off to infinity. So let's say this is y equals 2. Okay, I don't know. Okay, we've got this imaginary horizontal line. This function right here maybe equals 2.5. As we go out to like x equals 20, maybe it's now 2.1. As we go out to x equals 100, maybe it's 2.0001. And it's getting closer and closer and closer and closer. Now, it's not going to touch it as we're heading towards infinity, but we just keep getting closer and closer and closer to 2, and so our function kind of follows this imaginary line. Same this way. This time the graph is approaching from the bottom, and but again, it's getting closer and closer and closer. So maybe this is 1.9, and then as you go out, it's 1.99, 1.999. It's getting closer and closer and closer to that value. Okay? Now, you are allowed to cross a horizontal asymptote. You will never, ever, ever cross a vertical asymptote, but you are allowed to cross a horizontal. If you do, your graph usually does so in the middle, like not towards infinity. Okay, as you go towards infinity or negative infinity, your graph doesn't cross, but it can here in the middle. And sometimes we'll have graphs that'll do that, and I don't want you to get worried and think you did something wrong. Okay, an oblique asymptote is just a horizontal asymptote that has a slant to it. Okay, so this would be a line like y equals 2. Okay, a horizontal line. This one has some slope to it. So maybe this is, looks like it's going to hit way down here. So maybe this is y equals 2x, I don't know, minus 5. Just an example of what an oblique asymptote could look like. So it's going to have a slope to it as well as a constant, whereas the horizontal just has a constant. But the idea is the same. As you head towards infinity, your graph just starts to curve and follow this imaginary dotted line and get closer and closer and closer to that value. Okay? All right, so on the last page, over here on the side, you're going to see an example. This is a graph of a rational function, or just an example of what it could look like. And then we're going to come over here and we're going to answer some questions about this. We're going to find the domain and range of that graph, find any intercepts. We're going to talk about the vertical, horizontal, or oblique asymptotes that we may find. So the first thing I'm going to do, actually, I'm going to jump down here to like this vertical asymptote. This graph, you can tell, now it's kind of hard to see the dotted line. There is a dotted line right here, but since it coincides with the y-axis, it's hard to see. But you can tell by the way the graph is curving up, and then it's starting to go skyward, and then down here it's curving down, that this is a line that we are not going to cross. So the vertical line, the y-axis, which would be x equals 0, is going to be a vertical asymptote. Now, if you know that, then you should also know what the domain of this function is. If x cannot equal 0, or if x equals 0 is a vertical asymptote, that means our domain would be all the x's except x cannot equal 0. That must be a domain restriction. Okay, and you can tell from the graph, this graph is heading towards negative infinity. It goes up and then it curls. It does not equal 0. And then this side starts kind of at 0 and then it goes towards positive infinity. So that's our domain. The range, remember your range, that's your y values. Well, from bottom to the top. So this graph is pointing down. So this is heading towards negative infinity. So we got from negative infinity, and then the graph stopped. This is kind of a high point, and then there's this big gap where there's no graph. Okay? So this is kind of our highest range value. So from negative infinity up to negative 2. So from, I guess I could use interval notation here. So from negative infinity up to negative 2. And then there's a gap, a break, but then it starts again at 2 and goes to positive infinity. So that plus everything from 2 to positive infinity. That would probably be the easiest way to talk about that set of numbers. Okay, so that's the range. So you got your domain left to right, you got your range bottom to top. List the x and y intercepts. Well, there's no x-intercepts, and also since the y-axis is a vertical asymptote, there's not going to be any y-intercepts either, so there are none. Okay? Now, D and E say list the horizontal or list the oblique asymptotes. you can only have one or the other. You can't have both. So any graph can have a maximum of one horizontal asymptote or one oblique. You can't have two horizontals. You could have as many verticals as you want. I could create a function for you guys where you'd have like 5 different vertical asymptotes. I'm not going to, but I could. But any graph can only have one horizontal or one oblique, and not even both of those. Okay, so this one has an oblique asymptote. So we can see this diagonal line. If I wanted to write, see, they listed this point that the graph goes through, so we can kind of see what the slope of this is. This graph goes down 1, and then it goes over 1. So this has a slope of -1. It goes through the origin. So our oblique asymptote would be y equals, I'm going to write -1x plus 0. -1 is the slope. 0 is the y-intercept. I know that normally you wouldn't write that. You would just write y equals negative x. But for your notes, I just wanted to be explicit as to what was going on. Okay? So that's an oblique asymptote. Now, I told you how to find vertical asymptotes. So now we need to talk about how to find either horizontal or oblique. So notice I have the word or here. Okay? It's only going to be one or the other. So imagine you have some rational function. So you've got some fraction, and it's got some crazy looking polynomial on top and some crazy looking polynomial on the bottom. And we're going to try to figure out what the horizontal asymptote of this would be. Now this is just a generic way of writing polynomials. So we've got some number x to the nth power, and then some number x to the 1 less than that power, and then so on and so forth, down to a constant, and the same thing on the bottom. Well, here's the trick. First off, this is the only thing we're going to look at. So it doesn't really matter how big and crazy they make this function look. All we're going to look at are these two leading terms. And then even more importantly, we're just going to look at these two exponents, the n and the m. So n is the exponent of the numerator, and m is the biggest degree or the exponent of the denominator. So if n is less than m, if this number is smaller than this number, doesn't matter what they are, okay? Just if this is smaller than that, then the graph will have a horizontal asymptote at y equals 0, the x-axis. So if you have y, now let me write it as a function, f of x equals, and you've got some x to the 4th plus whatever, and then x to the 6th plus whatever, doesn't matter what's after that. The fact that this number is smaller than that means that y equals 0. Your x-axis will be a horizontal asymptote. That's it. That's rule 1. Okay? Rule 2. If n equals m, if these two exponents are the same, then the line a over b, which are your two coefficients, is your horizontal asymptote. Okay? So if I give you a function that starts out like, let's say 4x to the 3rd plus whatever, over 2x to the 3rd plus whatever, then the fact that these are the same, imagine that they cancel each other out, and then just look at these two numbers right here. Y equals 4 over 2, which would be the same as 2 over 1, okay, would be our horizontal asymptote. So y equals 2. So the line y equals 2 is going to be an imaginary line that our graph gets closer and closer and closer to as our x values head towards infinity and negative infinity. Okay? That's rule 2. Rule 3. If n is greater than m, if this is bigger than this by exactly 1, okay, by exactly 1, then you are going to have an oblique asymptote. And we are going to find the equation of that oblique asymptote by using long or synthetic division. Now I'm going to show you how to use long division because long division always works. Synthetic division, which we've used before, only works in special cases, and I'll explain that special case, but long division always works, so I'll show you how that works as well. Okay? And then I'll show you an example of how one that works like that. So if this is bigger than that by exactly 1, you're going to have an oblique asymptote. If n is greater than m by 2 or more, then there is no asymptote. Okay? So if you've got a situation where you've got x to the, 5th and you've got like an x to the third, then there's none. Okay, so this is almost a rule that just says there isn't anything. Okay, these three are the biggies. These are the important ones, and I'm sorry, but you're just going to have to remember them. You just have to memorize what the rule is and answer your questions that way. Okay, so let's look at example A. So down here, example A, I've got this rational function. I see that I've got an x squared and an x squared. So this is rule number 2. On your homework, I even do that. I even write down the rule. You don't have to. Okay, so rule 2 says that these are going to cancel, in a sense, and just leave us with y equals 2 over 1, which is y equals 2, and that is our horizontal asymptote, and we're done. There's nothing else to do on that problem. Okay, look at, let me go sideways. Look at C. I've got x to the 5th, and I got x to the 6th. So this is smaller than that. So if n is less than m, then that means y equals 0. So there's nothing to do here. Y equals 0, that is our answer, and we're done. That's all we're doing. Okay, B. Now example B, this is bigger than this. So that means we're going to have an oblique asymptote. This is rule, so this one was rule 1. This is rule 3. We're going to have an oblique asymptote. And so to find that oblique asymptote, you literally just take this and divide it by that. Now I'm going to show you how long division works. Long division, just like with numbers, you take the number on top and it's getting divided by the number on the bottom. So I'm going to do x squared plus 4x plus 1, and I'm going to divide it by x minus 2. Now, when you do long division, all you do is you look at your first term and you think, what could I multiply that by to equal that first term? So what do I multiply x by to get x squared? Well, x. Okay? And then you do that. You multiply. You take x times x, which is x squared, and you take x times, you have to distribute, you have to multiply that times everything, so x times negative 2, and you're going to get minus 2x. Now, the reason you want this to equal that, so I multiplied by x so I could get these to equal, is because when you do long division, your next step is to subtract. You're going to subtract what you just got as an answer from the previous step to see what is left over and then to do some more division. So x squared minus x squared cancels, so that's gone. And then here's where you're going to mess up, so don't do this. So 4x minus negative 2x. That minus distributes. Okay, so I put parentheses here so you'd see that. So 4x minus negative 2x is the same as 4x plus 2x, so this is a 6x. So that's what you got left over. So we got to keep dividing. Well, in long division, the next thing you do is you bring down the number that's left over, that's remaining, and then you do it again. So again, look at the x, and then you have 6x. So what do I multiply x by to get 6x? Well, a 6. 6 times x is 6x. 6 times negative 2 would be negative 12. You would subtract these from each other. These are going to cancel. 1 minus negative 12 is plus 12, so that's a 13. But actually, this is unimportant. As soon as I got this answer, that 6 right there, I was actually done. Y equals x plus 6 is the horizontal asymptote. This graph is going to have a line that goes through the y-intercept at 6, the y-axis at 6, and has a slope of up 1 over 1, up 1 over 1, up 1 over 1. And that's going to be this imaginary dotted line that we're going to draw because our graph's going to follow that. Okay? So let's take a look at D. Now, again, the top is 1 bigger than the bottom. So this is rule 3. We're going to have an oblique asymptote. Now, when you divide, so we're going to divide the top by the bottom. So I'm dividing 3x to the 4th. Now hold on. Just like in synthetic division, now synthetic division would have worked over here. If all you're dividing by is just like an x to the 1st power and there's not a number out front, you could use synthetic division. We would have used a positive 2, the number that would create a 0, and we would have used the numbers out front, and we could have done synthetic division. We would have got the same answer. But if you have an x cubed, an x squared, or if you have a number out front, a coefficient, then it doesn't work. So long division always works, so you might as well just do that. Now, you also have to account for anything that's missing. So 3x to the fourth plus 0x cubed minus x squared plus 0x plus 0. Go ahead and account for everything that's missing. And we're going to divide that by x cubed minus x squared. We're also missing an x. So x cubed minus x squared plus 0x plus 1. Now, this looks like it's going to be crazy. There's a lot going on. But just trust me, we're really only going to do two things. Once we have our x value and once we have our constant, we're actually done with the problem. That's our y-intercept, and that's our slope, and that's our oblique asymptote. Okay? So I'm going to look at this and say, okay, what do I multiply x cubed by? Just look at the first term. To get 3x to the fourth. Well, I need a 3, obviously. And then to turn x cubed into x to the fourth, I just need an x. So there's the first part of my answer. I'm halfway done, actually. Okay, so I have a slope of 3. It's going to be 3x, and it's going to be plus or minus something. That's the only thing we have to figure out. So 3x times x cubed is 3x to the fourth. 3x times minus x squared is going to be minus 3x cubed. 3x times 0x is just 0x squared. 3x times 1 is just 3x, positive. And then we subtract that whole polynomial from the one above it. So remember, we're subtracting. 3x to the fourth minus 3x to the fourth is, everything cancels, so nothing there. 0x to the third minus negative 3x to the third. So that's going to be positive 3x to the third. Negative x squared minus 0 is going to be minus x squared. And then 0x minus 3x is minus 3x. Okay, but again, all we're going to do is we're going to look at this first term, and we're going to look at this first term, and we're going to turn this into that. Well, this is... Sorry, the very end of my video cut out. So again, all we had to do was we had to make sure that whatever we multiply x cubed by to get 3x cubed, and then these are going to cancel and we're going to be done. So 3 times x cubed is 3x cubed. That's it. That's the magic number. 3x plus 3, that's our oblique asymptote. So y equals 3x plus 3. So this asymptote goes through the y-axis at 3 and also has a slope of up 3 over 1, up 3 over 1. And that's what we would draw to help us graph this, which is what our next step is going to be on our next day. Okay? So take a look at the homework and let me know if you have any questions. Thanks.